So we'll carry on and we'll have a look at example 15. And they're thinking of this in the textbook, and in a lot of textbooks they do think of these as different ways around, where you have to find the critical region, or you have a test statistic already and then you see if it's significant. But really, I'm hoping that we can start thinking of everything really as the same sort of method here. So let's have a look at the example. We've got a machine producing bolts of diameter D, where D is a normal distribution. So the diameter of these bolts should be normally distributed with a mean of 0.580 and a standard deviation of 0.015. So my variance is that squared. The machine is serviced, and after the service, a random sample of 50 bolts from the next production run is taken to see if the mean diameter of the bolts has changed. So this is just routine checking that the machine hasn't been changed in any way. We've no reason to suspect the bolts are getting bigger or smaller. We just want to check that they haven't got bigger or smaller. The distribution of the diameters of bolts after the service is still normal with a standard deviation of 0.015. So we're going to make that assumption that the standard deviation hasn't changed. We're just checking, has the mean changed? It's finding at the 1% level, usually 5%, they've gone for 1% just to change things up here, find the critical region for this test. So in other words, we are going to this machine, we've taken our sample of 50 bolts, but we don't want to just go in, take a sample of 50 bolts, measure them all. That's going to take quite some time, and then go, oh, there we go, the number's this. Now, is that important? Is that significant? We don't know. So before we go in, we know what number we're looking for, right? Well, what is our critical region going to be? But again, I'm hoping that we can just think of these as all the same sort of question. We have a null hypothesis of mean is still equal to whatever it's supposed to be, 0.58. We have an alternative hypothesis that the mean is different to 0.58. We have a sample mean which is distributed normally. Under the null hypothesis, 0.58 is the mean, and the standard deviation is 0.15 over, so the variance is 0.15 squared over 50. So 0.15 over the square root of 50 is my new standard deviation. Okay? Now, if we have a significant result, we're going to be significantly far enough away from 0.5 to be in the critical region. So let's think about this D bar distribution. It's centered on 0.58, and we have a critical region. It's a two-tailed test. So this area here and this area here have to add up to 1%. So this is half of a percent, so 0.005, and this is half of a percent, 0.005. Okay. So what number is this here? Now could you see what I'm trying to say? If we picture the distribution, we think about our critical region, we think, are we far enough away? Then once we've done that bit of thinking, we're using techniques from earlier in the chapter to answer that question. So we're kind of through the hypothesis testing part, and we're back into, well, how do I work out this value here? So again, the way I would say that is I'd say, well, what number's this here? Well, the probability that D bar is bigger than, well, let's call it little d. Bigger than little d is 0.005. Now, maybe you can run straight into your calculator and use these numbers. The way I would do that is to say that is the same as the probability that Z is bigger than D minus mu, which is 0.58, over sigma, which is 0.15. I'm sorry, I seem to have dropped a 0 there. 0.015 divided by square root of 50. So take away mu divided by sigma. The probability that Z is bigger than that needs to be 0.005. And this probability that Z is bigger than something equals 0.005 is something I can look up in a table, or again, maybe you go for your calculator. But that's something that we need to be able to calculate through the techniques from earlier in the chapter. When I get that, it turns out that value there is, let me see, I'm going to steal this one straight out of the book, minus 2.5758 and minus 2.5758. So D minus 0.58 divided by 0.015 over square root of 50 needs to be bigger than 2.5718. Bigger than or equal to, or bigger than, doesn't really matter. Okay, so we can work out the value of d from there, and then we need to do the same thing on this end of the test as well. Okay, and this will be d is going to be less than minus 0.25718. And when we solve that equation, it turns out here, let me just have a look, to be 0.5745 it looks like. Okay, sorry, 0.5745 is the lower limit, and there'll be an upper limit of 5854. So it turns out that if our if our d bar has a value between 0.575 and 585, then 0.585, then we're not going to reject our null hypothesis. That's where the critical regions fall. That d there is 0.585. This d here is 0.575. But look, I think the decimals are perhaps confusing things a bit. Let's just think about it this way. That value there is the probability that d bar is bigger than that value there. It has to be 0.005. Why 0.005? Because it's a 1% test and it's two-tailed, so 0.005 goes there. That's that area. That you can maybe find from a calculator, but the way I like to do it is to standardize. So d, take away 0.58 divided by sigma. Okay, that z value there is something we can look up or maybe find from a calculator. Once I know that z value is 2.5718, then that will help me find the d value. Okay, so I can look up that z value and I can put that in. Once I've found the d value, it goes there. We can do the same thing with less thans on this side, and that gives us our critical region is bigger than that and less than that. Our sort of non-critical region is between those two values. Okay. There is just one more thing to add, which is drawing conclusions at the end of the hypothesis test. So, if we fall in our critical region, we say this is a significant result, therefore we reject the null hypothesis. This test provides evidence to support the alternative hypothesis that. We don't say there is definitely a problem with the machine. We haven't proved there is a problem with the machine. We have collected evidence to suggest there may be a problem with the machine. The strength of that evidence depends on the circumstances of our test, the size of our sample, and all our other statistical processes. We can have a statistically significant result, which is still not good evidence because we didn't do the statistics well, we didn't collect the data well. We only took a sample of 3 bolts to measure with, and that sort of thing. So be careful about that. If you are accepting the null hypothesis, so if we have a non-significant result, then we say this result is not in the critical region, therefore we accept the null hypothesis. There is not evidence to support the theory that the alternative hypothesis is true, or we do have evidence to back up the theory that the machine is working fine and there is no problem with it. What we don't do is say the mean is definitely still 0.58. We can't say that for sure. We can say we have evidence to support that hypothesis. Okay, so you will know, I'm not quite sure yet how long all that ended up and how many videos I've cut it into, but there we go. That is the end of the statistics, and it's also the end of, for me, the end of this book, and it's the end of all 4 of these textbooks. That's the end of the whole A-level course. Once I've uploaded this lot, the whole lot's there. I hope that's been useful, and good luck with your A-levels.